Hey, in previous videos I explained how to make a RayMarcher from scratch, and I also explained how to make different distance functions so that you can make a sphere and a cylinder and a box and a plane and a torus. And in this video I will show you some operators that you can put on your distance functions in order to combine them in different ways or deform them in different ways so that you can make even more cool stuff. So let's get started. So I have here a scene with just a box in it, and over here I have my distance function for that. So basically I get the distance to the ground plane, then I get the distance to the box, and then I blend them together, and then that gives me that. Awesome. Now the first thing is, how do I move an object? Now and this actually goes for many different operators. We don't really change the function for the object, but what we do is we change the position of the point that we calculate the distance to. So with RayMarching, we have like we're marching along rays, right? So we have a ray that goes through the camera into the scene, and then there's a point that steps along the ray each time, and at each position we check what is the distance to the object. Now, like for movement, for instance, you could imagine that, well, we could move the box, but we could also just move that point, and if we move the point in the opposite direction, then that gives basically the same result. And now we only have to move one point. So that's basically what we're doing over here. So I want my box to be at this position. So I will just take my point P and I will subtract that position from that point P. So basically I move my point in the opposite direction so that my box appears moved. So that's just that's for moving stuff. So we could change this to whatever we want, and it will move the object. All right. So now let me just take this here. Let's cut it out, and let's call this box position BP. So now I have my vec3 here, BP, and that's just this. So nothing should have changed right now. So now I have a particular point that is just particular for measuring the distance to the box. So now what I can do to rotate it, for instance, I have this rotation function over here that rotates, or that returns a 2D rotation matrix, and I've just memorized this. Basically, it's like you put an angle into it, and then you get the sine of the angle, the cosine of the angle, and then you return this matrix. So C minus S and C. And now that we have that matrix, we can multiply that matrix by any 2D point, and it will rotate that point. So what we can do here is, well, so my BP is a 3D point. So what we can do is we could say, let's say we rotate only the X and Z component of that. So X and Z is the ground plane. So if we rotate around, or if we rotate these points, that's similar. That is similar to rotating it around its up-down axis. So kind of like this. So what we can do here is say times equals rot of I time, let's say. And now I have to press play, otherwise I can't see it. And now you see I have a rotating box. So we could do that around, basically the rotation is around the axis that isn't shown here. So right now it's XZ, so the rotation is around the Y axis. Similarly, I could have a rotation around the X axis by doing this. So now I have a rotation around the X axis. And I can rotate around both axes by just copying this. So let's say I first rotate around the y-axis, and now I'm going to rotate around the x-axis. So let's see what that does. So now it rotates around both axes. And let me just stick with one axis at a time. And order of operation makes a difference here. So like over here we we are translating before we're rotating. So that means that the rotation is local to the object. So if I move this somewhere else, then it will be moved, but it will still rotate around its own axis. If you don't want that, if you wanted to rotate it, let's say around a point that's outside of itself, then you would have to change the order of the operation. So what I could do here is, so p minus equals. So this is basically the translation, and this is the rotation. Okay, no, not p minus, bp minus, obviously. Okay, so if I do the translation before the rotation, then it will rotate around its own axis. But if I do the translation after the rotation, then let's go over here. I screwed something up. Hang on. Let's go back, cut it, and paste it. So now I have the order reversed, and now you see that it orbits around the origin. Okay, so you can play with that. Let me just put it back over here. All right, so that's rotation. Now there's different ways to do rotation. For most intensive purposes, like most of the time when I rotate something, I rotate it just around one axis. So if you rotate it around one axis, then this is just fine. So this function, you should really memorize this because this is used a lot. If you wanted to do really complicated rotation in any which direction, and it has to be precise, then there are different ways of rotating things. Then you might want to look in quaternion rotation. But yeah, for most intensive purposes, this will do just fine. Okay, so that's rotation. What else do we have? Yeah, we have scale. So for scale, let me just make a sphere instead. So let me just go over here and go float SD for sphere distance. So if you remember, the distance to a sphere is just the length of p minus the radius, right? And then we could do the same thing over here. So let me just do sphere position. So then I go over here, vec3 sphere position equals the position, and then like over here I'm going to do sphere position minus equals, and here I do the translation. So vec3 0, 1, 0, let's say, and let me just put this over here. It's a bit clearer. And then instead of my box, I'll just put my sphere distance. So let's see what that does. Okay, I forgot a semicolon over here. Okay, so there's my sphere. So we can do scaling. So in order to scale stuff, you could just multiply the position by some number. So I could do SP times equals 2, let's say, and that will make my sphere twice as small. And you can see already like an issue with this. But let me before we do that, let's multiply this by a non-uniform scale factor. So this basically scales it with like all three axes at the same time. But let's scale it a little bit different. So let's do this 1, 1, 1. So that shouldn't change anything. So that's just the original sphere. If I just wanted to, let's say, squash it from top to bottom, I can just do that, and now I have a squashed sphere. But now you see, when I get too high here, you see that, well, it's maybe hard to see here, but you see that something is happening here, which is wrong, and that is because now what can happen is that basically what this does is it stretches the distance field, and it makes the distance field kind of invalid, so that what can happen is that the RayMarcher is going to step into an object or even past an object. So I bet if I scale this more, yeah, see, like it gets really gets really shitty here, you see. And the reason why that is because the distance field is not, the distance field is stretched, and you can't like march properly through a stretched distance field. So we need to compensate for this, and the way to do that is like we have to get more conservative when we step through the distance field. So normally we step with certain step sizes. Well, this kind of invalidates the distance field, and therefore we have to decrease our step size in order to not overstep into an object or even past an object. And so we have to decrease the step size by the same amount as we squash the object. So here we squash it by a factor 4, right? The largest of these three numbers is 4. So what we have to do then is for our final sphere distance, we have to divide that by 4. So now you can see that now everything is smooth as a whistle, or clean as a whistle. Anyways, everything works again. Obviously, this makes your RayMarching slower. So any kind of operation where you kind of fudge the distance field so that you get potential errors, you can often get rid of those errors by making your step size smaller, but it also makes your overall performance lower. So wherever you can avoid that kind of stuff, then you probably should. Yeah. So like we need to divide this by the largest of these three. So if I had something that is whatever, scaled 3 in one direction and 5 in another direction, so let's say what that does. So that gives me some really squashed sphere. Then like in order to never get any issues like we have over here, we have to divide our distance by the largest of these three, so by 5 in this case. So there we go. All right, so that is translation, rotation, and scale taken care of. So let's get rid of this over here. Let's go back to that. All right, so now next thing we can do is something very interesting. That is Boolean subtraction. So you can subtract one object from another object. And let's just look at that real quick. So we have here a sphere, and then we have another sphere, and basically we want to subtract this sphere A from the sphere B so that we get this byte taken out, or over here you can see it. And so let's see what that is. So the formula for that is the maximum of the negative distance to A with the positive distance to B. And let's just see real quick why that is. So if we have a point over here and we want to RayMarch in this direction, and basically we want to like get to this surface over here. Let's see here. So if we're outside of A and outside of B, right? If point P is outside of either of these objects, then that means that dA and dB will both be positive, right? And that means that when we make this negative, that dA will always be smaller than dB, and so that means that this max thing will always give us dB. Okay, so if we are any point outside of A and outside of B, it will just trace the distance to B. Right, so if we look at that, this is the distance to B. Okay, so our next point is going to be right there. So now we have a different situation because now we're inside A, but we're still outside of B. Well, if we're inside A and outside of B, then that means that the distance to A is negative because we're inside of the object, and so. And we're still outside of B, so that is positive. So if dA is negative and we take the negative of that, so then it will be positive. So we have a positive number and a positive number. So if that is the case, then it will just take whichever surface is farther away. Okay, so from this blue point here to the surface of B is a very close distance, right? So only from here to here, but the distance to A is like somewhere over here. So that distance is larger. So it will take whichever is further. So it will take the distance to A. So my next point is going to be there. Okay, and now we have the third situation, which is when we're inside of A and inside of B. So that means if we're inside of A, then A is negative, so minus will make it positive, and B is negative, and so that will be negative. So if we're inside of A and inside of B, then it will always take A to trace. Okay, so now we trace to A, and now we get to our point. How neat is that? So let's implement that. Okay, so I have my, let's see here. Let's just put it all in one here. Yeah, let me just clean this up again so that we have it all on one line. Okay, so that shouldn't change anything. Okay, it's the same thing. So this is, let's say, SDA, and then I'm gonna do the same thing for an SDB. So SDA and SDB, and okay, and now I'm gonna make float SD equals. Let's just first put them both in, so I can position them. So I'm gonna do the min of SDA and SDB. All right, and now I have to obviously move one of them here. So let me just move it. Okay, so now we have two spheres, and so now let's subtract one from the other. So instead of doing this min, I'm going to do max, and then I'm going, no, not here, hang on, over here. Max, and then in order to subtract A from B, I'm going to do minus A and B. So now we have a nice bite taken out of it. So you can see this is very powerful with these kinds of operations. You can make a lot of very cool things. So that is Boolean subtraction. Now we have another thing which is called Boolean intersection, and so what that is, if you have a sphere A and a sphere B, instead of taking a byte out of sphere B, we just say, okay, only show us where they both intersect, where they both overlap. So how do we do that? Well, that is just the maximum of dA and dB. So let's walk through that real quick. So we have our point P over here. We want to trace. So if we're outside of A and outside of B, then it will just take whichever one is further away. So in this case, B is further away, so it will trace to B, and then we're over here. And now if we're inside A or inside B, so we can either be inside either of them, but not both of them. So if we're inside either of them, then like let's say it's inside of A, well then my A will be negative, and so then it will always take the other one. So it will, if it's inside A, inside B, it will take whichever distance it is the P is still outside of. So in this case, it's still outside of B, so it will take the distance to B. And that is how you get the intersection. So let's make that. So simple enough. I could just get rid of this minus over here, and now I have an intersected shape. Okay, the next thing is a union between two objects. So if we have two objects, A and B, we want to merge those objects into one. And the way to do that is by just doing the min of A and B. We've already seen it before, because if you ever have more than one object in your scene, you're already doing a union. So we're already using this min. But let's just go through it real quick anyways. So we have a point P over here, and we're marching in this direction, and we're just taking the minimum of either object each time so that we can never step into either object. Okay, fair enough. Now over here you see a nice smooth union between two objects. So how can we do that? Well, let's have a quick look at it. So let's look at it over here. So this was still our intersection, so let's put it back to a union. So that is with the standard min function. Well, there is also a function you can make that gives us a smooth minimum between two objects, or between two functions really. I did a separate video about that, so if you want to know how this works exactly, then go check that out. But for now, I'm just going to implement it, or well, it's already implemented, but I'm just going to use it. So instead of min, I'm going to do smin, smooth min, and smooth min takes a third parameter that tells us how smooth the intersection should be. So watch what happens to the to the edge between the two objects over here, and you see that it disappeared. That's amazing. So you can make that sharper if you want, or you can make that more smooth if you want. And maybe with two spheres it's not super obvious. So let's look at a box and a sphere. So let me just put the box back. So there's my box. Let me just make sure that the box is at 0, 0. Okay. No, actually that's not. Let me still put it off to the side a little bit, and then let's use this SD over here. But then instead of going between the two spheres, I'm just gonna go between the sphere and the box. So now you can see that we have a smooth merge between those two objects. I can move it maybe farther away a little bit. How cool is that? So you can see that this is very, very powerful, especially if you want to do organic modeling, if you want to, I don't know, blend a tree into the ground or something like that, then this smooth minimum is really, really powerful for that. All right, so the last thing I'm going to show you is how to morph one object into another object. So what we can do here is, let's see here. So let's put my box in the middle again, and now instead of a minimum function, we're going to use a mix function to mix between the two distance functions. So we have the sphere distance functions over here, and we have the box distance function over here. And now what I can do is, let's say, like blend between the two. So let's just do, let's say this, and now we have a sphere blending into a cube, blending into a sphere. So these were a few very useful operators for distance functions. And so as we go forward, we're slowly building our toolkit, like full of tools that we can use to make really, really cool stuff. If you like this, please like, comment, subscribe, click the bell icon. If you make anything cool, I would love to hear about it, so post it in the comments below. And either way, I will see you next time.